5.2 polynomials, linear factors, and zeros. So in this section, we're going to get into a little bit more math, a little bit more algebra. But again, it's a ton of vocabulary. And a lot of those vocabularies are based off of what we are seeing in this picture here. So a polynomial is going to be a graph. It's going to look like a quadratic or something like this that has peaks and valleys, and we can look at where it increases, decreases. And we have these values here that are really important. And these factors, or these values right here that hit the x-axis, are called our zeros, okay? So the zeros are where the graph crosses the x-axis. Very important points. You're going to be asked to find zeros. You literally just find where the graph crosses the x-axis, and you can do that on Desmos, or you can do that on your graphing calculator. And then we have these points right here, which are called maximum and minimums. And we call them relative maxes and relative mins because they're not actually, this isn't the highest point of the graph. It goes up, 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 up. And this isn't the lowest point. It continues to go down, 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 down. But it's a turning point. And at a turning point, we either have a maximum or a minimum, and they're important values for when we get into some word problems or things that help us find certain values. Those are our important points. So we're going to go through a few problems here. We're going to talk about, zeros and factors and things like that. But given a problem like this and just kind of going off of what we did in chapter 4, this says, what is the factored form? Well, I need to take out a GCF. So of this problem, I can take out an x. That would leave me with x squared minus 2x minus 15. And then now this quadratic, I know how to factor from chapter 4. I'm looking for two numbers that multiply to negative 15 and add to negative 2. Okay, two numbers that multiply to negative 15 are negative 5 and positive 3. So this would be the factored form of this polynomial. This one, same thing. I'm going to take an x out. It will leave me with x squared minus x minus 12. And I'm looking for two numbers that multiply to negative 12 and add to negative 1. So it would be x minus 4, x plus 3. And this is important because these are called linear factors. Okay? These are called linear factors. In this problem, if I asked you to solve the polynomial, it was set equal to 0 or find the x-intercepts. They would be x equals 0 using the zero product property, x minus 5 equals 0, and x plus 3 equals 0. This would be x equals plus 5, x equals 5, subtract 3, x equals negative 3. Okay, so the zeros or the solutions would be 0, 5, and negative 3. And if I were to graph this polynomial, it would cross the x-axis at 0, 5, and negative 3. That's why factoring is so important, because I can write these as linear factors and I can find the zeros or where it crosses the x-axis. So if I gave you this problem, and I'm just going to go through it real quick, we're not going to graph this, but it says, what are the zeros of y equals? And this right here is a polynomial. It would have a 0 at negative 2, at positive 1, and at 3. So I'm telling you that this graph would cross at these 3 points for the graph. Okay, now it's going to do a bunch of different other things through here, and we could graph it to get a picture of it. But just using the zero product property, I could find where each of these cross the x-axis. Okay, so zeros are where the graph crosses the x-axis. If I have a 0, I can write a factor. If negative 2 is the 0, the factor is x plus 2. So the 0 is always the opposite when it's given a linear factor where there's no number in front of the x here. Okay, so again, in this problem, what are the zeros of this function? I don't even need to graph it. I've got an x here. I can set x equal to 0. I can set x minus 3 equal to 0, and I can set x plus 5 equal to 0. This is a 0. Add 3. X equals 3. Subtract 5. X equals negative 5. So this would cross at negative 5, at 0, and at 3. There's my 3 zeros. Now, I want you to look, if I gave you a problem that looked like this, and we did some of these last chapter, it's always the opposite of these. But because this doesn't have an x, that would not be a 0. This has nothing to do with zeros. The zeros for this would be 2 and -5. And again, you could always plug this into Desmos or your graphing calculator and graph it and see where it crosses the x-axis. But I'm telling you, it's going to cross at 0, at 3, and at -5. Okay, so the expression x minus a is a factor of a polynomial if and only if the value a is a 0. So that's what I'm saying. I need you to be able to take any factor and write it as a 0, and any 0, write it as a factor. So if I give you a cubic polynomial, okay, a cubic polynomial is going to have 3 zeros. You're going to have the same number of zeros as you do the degree. So if -2 is a 0, its factor is x plus 2. You just put an x in front and change the sign. For 0 of 2, I put an x in front, I change the sign. And for 3, I put an x in front, I change the sign. So these would be the 3 linear factors given these 3 zeros. Now I want you to write it in standard form, which means I need to multiply. So I'm going to multiply 2 of these together first. X times x is x squared. X times -2 is minus 2x. 2 times x is plus 2x. And 2 times -2 is -4. I'm going to combine like terms. So I haven't done anything with the x minus 3 yet. Now we get x squared minus 4. Notice there's no middle term because they cancel, times x minus 3. So I'm going to multiply these now. X squared times x is x cubed. I'm going to multiply every term by every term. X squared times -3 is -3x squared. -4 times x is minus 4x. And -4 times -3 is a plus 12. So this would be my cubic in standard form. So you're going to be given some problems that you have given zeros, you have to write them as factors. And again, to write them as factors, you put an x in front and you change the sign. So this is a really important topic of this. Now, there's going to be times where, again, if you have a 4th degree polynomial, you should have 4 zeros. If you have a 3rd degree polynomial, you should have 3 zeros. If you have a 2nd degree polynomial, you should have 2. There's times, though, where the graph doesn't show that there is that many zeros. So if I had a problem like this, okay, and I multiplied this out, I would have 3 zeros. I would have a 0 at -2. I would have a 0 at 2 and a 0 at 3. So I'd get 3 zeros. Here, this x plus 2 squared means x plus 2, x plus 2, x minus 2, and x minus 3. The zeros would be -2, -2, 2, and 3. These are the same 0. You're not going to see them twice. So actually, it's called a multiplicity. And something special happens in a graph. Okay, if there's multiplicity, the graph appears to like bounce off at the x-axis. So if I were to go to Desmos here, okay, and I were to plug this in, this problem right here, which said, what's x to the 4th minus 2x cubed minus 8x squared. So x to the 4th minus 2x cubed what was it, minus 8x squared. I think what it was. Okay, you can see that it has a 0 at -2, a 0 at 0, and a 0 at 4. But because this is a 4th degree polynomial, it should have 4 zeros. Well, if you look at this graph, do you see how it bounces off at 0? That means there's a multiplicity 0 there, and it counts as more than 1. Now, how many does it count as depends on how many more zeros I need. If I have a 4th degree polynomial, I need 4 zeros, which means there's 1, there's 2, 3, and this would count as a 4th, so the multiplicity would be 2 there. Okay? So there's multiplicity of a graph. What are the zeros of the following functions? So again, take this and graph it. So x to the third, nope, that's not what I wanted yet. X to the third minus 4x squared is it minus 4x, I think, or plus 4x. Okay, so I graphed this and I want to know where the zeros are. Well, I only see 2, but I know I should have 3 because it's a third degree. The zeros are at 0 and 2, and what happens at 2? It bounces off, so that would be multiplicity 2. So we would say, for this problem, the zeros are, okay, the zeros are 0, 2, and this has a multiplicity of 2, or you could just say 0, 2, and 2. Okay, so again, at the 0, because there's just 1 at 0, it goes through it. At 2, it bounces off. That's what happens when there's multiplicity. Okay, there's also times where the graph will do something like this, where it doesn't necessarily change direction, but like it kind of like flattens out. So it looks something like this. This would be a multiplicity 0 as well. And we'll look at some examples that look like that. So we talked about the turning points in 5.1. Now these turning points are called a relative max or a relative min. And through the graph, we just call them the turning points, but they're important points for us to be able to find. So a relative min is, again, when the graph goes from decreasing to increasing, and it's not the actual minimum. If I had a graph that looked like this, okay, I would have a max, a min, a max, but this would actually be the max because it's the highest point, and this would be called a relative max. It's still a turning point that creates a high point, but it's not the highest point. Okay, so relative max and relative min, and again, in Desmos, they're really simple to find. You just click on them and they show you where the relative max and where the relative min are. So I want to look at just a couple problems. One of these problems that finding the features. So it says the polynomials graph below. It says the degree of the polynomial. Now to find the degree, I'm going to ask you if it's either even or odd. It's even if it's going up and up or down and down. If both of the end directions are going the same way, then it would be even. Because this is not going up and up or down and down, then the degree of this is odd. Okay, now a normal odd parabola will always start increasing and finish increasing if it's a positive leading coefficient. So because this is starting going down, this is a negative leading coefficient. Okay, a normal graph would go up and continue to increase through the beginning and the end. Okay, now there are how many real zeros? How many real zeros are there? How many times does it cross the x-axis? 1, 2, 3, 4. So there are 4 real zeros. And how many relative extreme values, meaning how many min and maxes? 1, 2, 3, 4. Okay, so I want to look at this and make sure that this gives me the correct answer, because what do we notice here? It bounces off, so that's actually counts as a multiplicity 0. Okay, but you don't have to add that multiplicity. It only crosses at those 3 places. Okay, so you've got some problems like this. Again, I want to look at one like this. Okay, so this one's going down and down, and because they're both going down, then this would be an even exponent. And because it's down and down, the coefficient is negative. If it was going up and up, the coefficient would be positive. And then how many real zeros? 1 and 2. How many local extreme values? Just this one right here. This doesn't give you a true turning point here. It just kind of flattens out. You have to actually see the turning point. So it only has one extreme value. Okay. So there's some problems like that that do that. And then again, determine the number of x-intercepts. So this is important to look at. If I have a problem that has x squared plus here, that's not going to give me real zeros. That's going to give me imaginary. So this is saying how many x-intercepts would I have? You could easily graph this, but you also can look at how to solve this. So this problem right here would have doing actually, I'm just going to go ahead and put that on there. All right, so let's look at this problem right here. How many x-intercepts does it have? And again, we're going to graph this in a second, but I want to show you that I could do, for each one of these, I could set each factor equal to 0 and solve it. So I could set 6x plus 1 equal to 0. I could set x squared minus 2 equal to 0, and I could set x squared plus 16 equal to 0 and solve it. This is back from stuff from chapter 4. I could subtract 1. 6x equals negative 1, divide by 6, x equals negative 1 over 6. So there's a real 0. I could add 2. X squared equals 2. Take the square root of both sides. X equals plus or minus square root of 2. There is 2. So right now I have 1, 2, 3. And then here, subtract 16. Now here's where you got to pay attention from chapter 4. When I take the square root of a negative, what happens? This would be plus or minus 4i. You're not going to see that on a graph. So I would only have 3 real zeros for that problem because these two are imaginary. So it's asking how many x-intercepts would the function have below, and it's 3. Okay. And again, in looking at that, if I went to Desmos and I plugged it in, and you can literally plug it in exactly like it shows. Okay. What was it? 5, 6x. And why didn't this one have a 0? Because it doesn't have an x. It has to have an x next to it. Sorry. Did you type it incorrect? All right. That's what it was. So if you look, here's the 1, 2, 1, 2, 3 zeros. Okay. And that tells you that's the simplest way to do is just punch it in the calculator.